In this video, we're going to look at transfer functions, and we're going to analyze the poles of them to determine what the natural behavior of the system is. And then we're going to go one step further and analyze the stability of the system before we add our control system to it. Now, just remember that the poles are nice and simple in some sense. They are the zeros or the roots of the denominator for our transfer function. And so literally what we have to do over here is just figure out what the roots are. Fortunately, there's a function in Python called roots. So we're going to build the roots. The only issue is syntax. When we have polynomials like this, you can look up in the help menu, or you can flash back to when we did the transfer functions themselves. We don't put s's in there because the s is sort of arbitrary. What we do put instead is the coefficients, because those determine the polynomial that we're talking about. So we have 1s squared, 8.4 s's, and then 22. So in a decreasing order, those coefficients are simply 1, 8.4, and 22. And what we get out of that are the roots. So two ways to look at this. If we go back to here, pardon me, if we go back to here, we can expand this. And remember that if we find a root, that's the same as saying that s minus that value is a factor. And we're going to round this to 1 decimal to 2.1, and we're going to call it I. And put brackets all the way around that, and s minus 4.2 minus 2.1 i's, and the numerator would not change. Now this factored form can lead us through several different chains, but honestly it's always the same process. So if you remember from the table of transforms, if we have an 1 over s minus a, which is what we have here, when we do the inverse Laplace transform, what we're going to get is e to the at. So here the negative 4.2 plus 2.1 i's times t. And then we're going to get e to the negative 4.2 minus 2.1 i's all times t. Nobody likes that. So if you flash back to first year calculus and Euler's formula, if you remember the rules that apply to, or the expansion we can apply to these complex values, more specifically the purely imaginary values, those imaginary values turn into cosine sines. So what we get out of this is another alternative, which is e to the minus 4.2t times cos of 2.1t. Or the other building block in our natural behavior is going to be e to the negative 4.2t sine of 2.1t. And that's it. Now, what you'll often hear as the last step in these types of analyses is this stable or unstable? And honestly, this just boils down to the exponential. The exponential has a negative coefficient. This is a decay. And so this all heads towards 0 as time increases, as t goes to infinity. And so it is going to be stable. Okay, that's the gist of it, honestly. What we might say, more specifically, we can actually say the poles are at negative 4.2 plus or minus 2.1 I. That would be the actual, where are the poles on this system? This will also lead to, we're not going to make a big deal of it here, one of the quick and dirty analyses of poles, and they're going to say, if the pole is in the left half plane of the imaginary, whatever, if you graph these points on the complex plane, negative 4.2, 2.1, there we go, the one in the middle, sorry. We're going to have 2 points out here. Guess what? They're in the left half plane. That's not that interesting in itself. What it actually means is the real part, the negative 4.2, ends up in an exponential. If that exponential is negative, things decay. Well, where do we get negative real parts? Over here in the left half plane. So you'll often hear that phrasing about the placement of the poles and which half of the plane they're on. What it boils down to is just, do you get negative exponentials or positive exponentials? So let's do the next one in a little more efficient fashion, what we're going to do is actually add a print statement around this so we have them all when we need them later. And there we go. And so for this one, we're going to print the roots of, again, the denominator. So just the coefficients are all we need. And that should be it. There we go. Negative 3.1 and 0.5. So the poles are at, we should call these Z values. Sorry, these are S values. S is equal to negative 3.1 and 0.5. These are the simpler cases. These lead directly to, because they're real, e to the at. Sorry, let me do one extra thing in between. If you wanted to recast it like this, you would be rewriting this as negative 4.3 over s minus negative 3.1 and s minus 0.5. So that would be the factored form. These are 1 over s minus a forms. They lead directly to exponentials. That's the step missing in between there. And so the mathematical forms you're going to get are e to the negative 3.1 t's and e to the 0.5 t's. Final question, is this going to be somewhere stable, or is the system going to be stable or unstable? Well, all it takes is just one element of this to have exponential growth, because we have a positive exponent. And so as soon as we have one of those, it doesn't matter what anything else does, because this solution is going to grow infinitely large over time. So we'd say this system is unstable. Last but not least, we'll do one more in the same vein. This time it'll be a cubic. Why not? Nothing fundamentally changes in the calculations here. We're just going to do the roots of s cubed is coefficient 1. The next highest coefficient is s squared, so 5.1, 2.75, and 11.26. We run that, and we'll do some rounding here. So we get the poles at s equals negative 5, and basically plus 0j, so we can ignore that. The other ones are complex, so negative 0.05 plus or minus, let's call it 1.5 i's. So the forms of the natural behaviors are going to be e to the negative 5t, and again, it's the real part if we have a complex one that defines the exponential, e to the negative 0.05t, cos 1.5, the imaginary goes in here, and e to the negative 0.05t, let's get that in here, sine of 1.5t. Oh my goodness. We have a cubic in the denominator that leads to 3 possible factors, 3 roots, and so we have 3 solutions in our set here. Now here, we definitely have 3 negative exponentials. However, this is where you get into the fuzzy region. This one here is pretty small. And so if you think about what a very close to 0 coefficient represents, this one is going to be a very gradual decay, slow decay. And so if you were thinking about, setting up the control system for a quadcopter or a drone or a rocket ship, and you said, well, I want this rocket ship to follow this path, but your rocket ship gradually approaches the path over like 5 minutes. You're like, that's not quite stable in my book. So for these kinds of cases, we would make an argument that this is called marginally stable, because there are some of these functions that decay, but only slowly. Only very slowly. Again, that's a judgment call. A lot of this would depend on the units you're interested in. If these are planets, who cares about this? But if this is something that happens in microseconds, this is going to be way too slow a decay to be practical. At the end of the day, you're just looking for the magnitude of this coefficient. If they're all negative, but one of them's pretty close to 0, we'd usually call that marginally stable. Okay, so that is how you would look at a transfer function and go, what is this telling me? It's telling you a whole story about the natural behavior of the system, and most of that comes from looking at the poles, looking at the complex values or the real values that come out of that, and then interpreting that as mathematical form. So right away you can predict that this graph here actually would have cosine sines. So it would be oscillations that are decaying very slowly, or one possible very rapid decay, but that's not all the behaviors. You have to sort of look for the worst case when you're talking about stability. Now it's worth mentioning that you've seen this kind of analysis before in 202, 203 mech, and this is when you looked at systems of differential equations. Here we call it the state space as the control theory idea. And that's simply looking at x as some vector of states, and then you have all these matrices in here to quantify what the system is doing, just like the transfer function is one way to quantify or what defines the system. So here we'd have four matrices that define the system. Again, x is our state, and it's got the derivative of x equals some a times x plus the control times b. And then these other factors, again, you'll see those more in a control theory course, but have to do with maybe what you can measure, this value here, y. But for us, the important thing to remember here is if we're talking about what kinds of solutions come out of this, the only thing that matters is the a. Because the b's don't matter, the u's don't matter, because we're saying what's happening in the uncontrolled system for the natural or uncontrolled behavior, so we ignore the control u. And we don't really care so much about the observer part. We actually care about the dynamics of the system, what kind of functions are going to show up in our x's, and so we can just focus only on the a. The other elements are just a distraction when you're starting. Sorry, the sticking noises were coming from my cat scratching at a box. All right, so what about the A matrix tells us what we need to know? Well, this goes back to eigenvalues and eigenvectors. I'm not going to go through the details of this. I'm just going to remind you of how to compute that in Python. But if you look at the eigenvalues of this system, it will tell you essentially, in fact, identically, the information that you get from the poles for the transfer function. The two system definitions are or can be made equivalent to each other. So in particular, let's take a look here. And what we're going to do is enter our matrix. So we're going to say A is equal to an array of 0 and 1, and then another array on the next row of negative 8.4 and negative 22. And we're going to run that. So if we go to calculate the eigenvalues and eigenvectors of this, let's call them v and w, are what we get when we do the numpy. And the only issue is you have to slide a little linear algebra in here by default. And then you can say, what are the eigenvalues and eigenvectors of A? And of course, we need to display them when we're done. So just for the sake of argument, we'll print both of them, because sometimes it's not clear which one's which, but it'll be more obvious when we display them. Perfect. So V and W, V comes out as a vector of just two numbers, and the W comes out as a matrix. Its columns would be the eigenvectors that we might be interested in other circumstances. But for today, it's these two values here, the negative 3 and the negative 21. So the same logic would apply as to the poles. Here we get the eigenvalues that are lambda equals negative, I'll call it 0.4 and negative 21.6. So right away, the mathematical forms are here. The assumption is that our solution x equals some vector e to the lambda t. Once we have our lambda, we build out the solution like this: 0 to the e to the negative 0.4 t, or e to the negative 21.6 t. That's it. And then this one, this is definitely stable. But this one, this would be one of those in-between cases. Stable, marginally stable, hard to say. Let's say marginally stable, because it's still fairly close to 0. Again, it would depend much more on the context of how quickly does this decay when we look at a graph, and how long is, 1 second of time in our particular context. Let's do the same thing again here. For simplicity, I just shifted the numbers around so we don't have to keep recreating big matrices. But we have negative 22 and negative 8.4. And here we have again the eigenvalues the lambda values are negative 4.2 plus or minus 2.1, it looks like, 2.1 i's. Oh, actually I saw those earlier. Let's take a look back up here for a moment. That was in fact our first example here, and it's worth taking a look and seeing where this comes from, or where this could have come from. This could have been a spring system with a mass of 1, a damping coefficient of 8.4, and a spring constant of 22. That would have led to this expression in the denominator for our transfer function. And if we take a look at the state space system, where we would have had x double prime times mass equals minus cx prime minus kx. I'm actually going to put them in the opposite order because we list position first typically. Minus kx minus cx prime. Oh wait, minus k minus 22 minus the 8.4, exactly the same coefficients. So this is exactly the same system, represents exactly the same system as the first example we did up here, up to the numerator. Why do you care? Just to remind you that these two methods are equivalent. If you go through the physics and end up here, you'll be calculating eigenvalues that define the behavior of the system. If you went the other way and used physics to define the system and then went for transfer functions, you'd also end up with poles, but they're equivalent. The poles and the eigenvalues end up doing the same thing, representing the same thing. So again, the form of the solution here is going to be e to the negative 4.2t, and the imaginary part ends up giving us coses and sines. 4.2t sine of 2.1t. And so that's what we've got, and this is definitely stable. We have nice, quick exponential decays associated with both of those oscillations. So there we go. This is how anyone in control theory would look at the system forms, whether it be state space form or whether it might be transfer function form, and can get some important information about the system with some quick calculations, mostly focusing on the roots or the eigenvalues of the two forms. And that tells you a lot of information about what the system will naturally do. And then you can ask, well, how can I tweak that a little bit by applying a control later on?